Why does time change when traveling close to the speed of light? Imagine you are in a car driving across the country, watching the landscape. A tree in the distance gets closer to your car, passes right by you, then moves off again in the distance behind you. Of course, you know that tree isn't actually getting up and walking toward or away from you. It's you in the car who's moving toward the tree. The tree is moving only in comparison, or relative, to you. That's what we physicists call relativity. If you had a friend standing by the tree, they would see you moving toward them at the same speed that you see them moving toward you. In his 1632 book Dialogue concerning the two chief world systems, the astronomer Galileo Galilei first described the principle of relativity, the idea that the universe should behave the same way at all times, even if two people experience an event differently, because one is moving in respect to the other. If you are in a car and toss a ball up in the air, the physical laws acting on it, such as the force of gravity, should be the same as the ones acting on an observer watching from the side of the road. However, while you see the ball as moving up and back down, someone on the side of the road will see it moving toward or away from them, as well as up and down. Albert Einstein much later proposed the idea of what's now known as special relativity to explain some confusing observations that didn't have an intuitive explanation at the time. Einstein used the work of many physicists and astronomers in the late 1800s to put together his theory in 1905, starting with two key ingredients: the principle of relativity and the strange observation that the speed of light is the same for every observer, and nothing can move faster. Everyone measuring the speed of light will get the same result, no matter where they are or how fast they are moving. Let's say you are in the car driving at 60 miles per hour, and your friend is standing by the tree. When they throw a ball toward you at a speed of what they perceive to be 60 miles per hour, you might logically think that you would observe your friend in the tree moving toward you at 60 miles per hour, and the ball moving toward you at 120 miles per hour. While that's really close to the correct value, it's actually slightly wrong. This discrepancy between what you might expect by adding the two numbers and the true answer grows as one or both of you move closer to the speed of light. If you were traveling in a rocket moving at 75% of the speed of light, and your friend throws the ball at the same speed, you would not see the ball moving toward you at 150% of the speed of light. This is because nothing can move faster than light. The ball would still appear to be moving toward you at less than the speed of light. While this all may seem very strange, there is lots of experimental evidence to back up these observations. Time dilation and the twin paradox. Speed is not the only factor that changes relative to who is making the observation. Another consequence of relativity is the concept of time dilation, whereby people measure different amounts of time passing, depending on how fast they move relative to one another. Each person experiences time normally relative to themselves. but the person moving faster experiences less time passing for them than the person moving slower. It's only when they reconnect and compare their watches that they realize that one watch says less time has passed while the other says more. This leads to one of the strangest results of relativity, the twin paradox, which says that if one of a pair of twins makes a trip into space on a high-speed rocket, they will return to Earth to find their twin has aged faster than they have. It's important to note that time behaves normally as perceived by each twin, exactly as you are experiencing time now, even if their measurements disagree. You might be wondering, if each twin sees themselves as stationary and the other as moving toward them, wouldn't they each measure the other as aging faster? The answer is no, because they can't both be older relative to the other twin. The twin on the spaceship is not only moving at a particular speed where the frame of references stay the same, but also accelerating compared with the twin on Earth. Unlike speeds that are relative to the observer, accelerations are absolute. If you step on a scale, the weight you are measuring is actually your acceleration due to gravity. This measurement stays the same regardless of the speed at which the Earth is moving through the solar system, or the solar system is moving through the galaxy, or the galaxy through the universe. Neither twin experiences any strangeness with their watches as one moves closer to the speed of light. They both experience time as normally as you or I do. It's only when they meet up and compare their observations that they will see a difference, one that is perfectly defined by the mathematics of relativity.